Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you learn how to identify tangential and centripetal accelerations and to draw the vectors accordingly. So I'm going to go ahead and change my color to red. So what we're looking at is this, what we're looking at is this child kind of swinging back and forth here. And what you have to realize is that there are two types of accelerations going on here. You have tangential accelerations, and these have to do with changes in speed. And centripetal, or what are also called normal accelerations, and those have to do with changes in direction. And we're talking about the velocity vector direction. So at the end point right here, just for an instant, the child isn't moving, but the child is in fact accelerating because an instant later the child is moving. So there's going to be a tangential acceleration vector that points something like this. But there's no centripetal at the end point because, remember, centripetal acceleration, when you calculate it, it's equal to v squared over r. And there's no v at this point. The child isn't moving. Okay, this intermediate picture, this one, you have to ask yourself, is the child still picking up speed? And if you realize that from an energy standpoint, the potential energy is still dropping, the answer is yes. So there is a tangential acceleration, again, tangent to the curve. Now you notice I drew that vector a little smaller. And that's just, I'll just say for now, gut instinct. And in another video that's a little more detailed, I'll talk about how I know that. But the child is also undergoing a circular motion at this point. So there's a centripetal acceleration that points this way, up towards the center of curvature. Okay, at this location, if you think about the forces acting on the child, everything's vertical. There are no horizontal forces if you throw out air drag at that location. So now the only acceleration is centripetal, and it points this way. And you notice I drew that larger than this vector. That's because the speed at the lowest location would be higher. And remember, centripetal acceleration is speed squared over radius. Okay, so now at this location, again, the child is moving, so there still is a centripetal acceleration towards the center of curvature. But the child is now slowing down. So when I went through this, this entire example, I was going for motion in this direction. I don't think I made that clear at the beginning, but so because the child is slowing down at this location, the tangential acceleration vector points this way. And then at the highest location here, the child again is not moving at that spot, so there's no centripetal acceleration, but there is a tangential acceleration in this direction, right? So these are the two different types of acceleration that are occurring as this child swings back and forth. At any given time, the net acceleration is the vector sum of the two. And I think what I'll do is save that for another video. I hope that this helps demonstrate the difference between tangential acceleration and centripetal acceleration. Have a great day.